Welcome. So what this lecture course is going to attempt to do is give you an overview of what is going on currently in this field called collider physics, and also to give you an introduction to the technical skills that you need to be able to understand the data that is being taken currently, and how to understand or map that onto the theoretical understanding of what physics is and what is it telling us about the fundamental truths about our universe. Okay, so that's the big goal of this class, and then the smaller goals will be just to go through all of the details one by one. Okay, so just before we start, there is some useful information. So we've had to change the timings a bit to avoid overlap with the quantum field theory course that is also being run in the same semester. So the course will now run on Mondays and Wednesdays, and these are the timings. There should be about 25 lectures in the term. We will break if there are any big holidays like Holi or something, but otherwise we should be meeting every Monday and Wednesday. Okay. So yeah, we'll be using both pen and paper calculations and some computational calculations. The computational calculations will use either Python, Jupyter notebooks, or you can directly use Pythia. Okay? So Pythia is one of the codes that is very popular in collider physics. So we will talk about that more in detail. All code that is shown in class will be shared with you, so you can use it, modify it, do whatever. And for people from TIFR who are planning to credit the course, there will be in general 4 assignments, a midterm and a final. Then you can email me for any queries. I hope most of you have also signed up on the mailing list. So there's a Google group mailing list where we can share everything. So if you haven't, please just send me an email and I can add you there as well. Okay. Okay. So this is something mainly for people who are crediting it. So the homework and exam philosophy here is that this is not a competitive exam. Your goal is not to show how much better you are than your fellow students. The goal of this course is to get you up to date to work as a professional in particle physics or collider physics. Okay, so the exams are designed so that to test how much of the material you have learned, not necessarily to compare you with other students. So you are always allowed to discuss homework problems with people. Please do, that's very helpful. In fact, if you are a professional scientist, you almost never work alone, you always work in a collaboration. So you will just get used to talking to other people about physics. And if you write something up together, so if you're solving a problem together, writing code together, please mention the people that you've been working with. Okay, so that's perfectly allowed. You can work together with people. But what is not allowed is just copy pasting somebody else's work and submitting it as your own. Okay, so if you submit that, you will participate. Okay. So now we can come to the interesting parts of this course. So this is the main goal of the course, that the details of what I was talking about. So the first thing that we want to understand is how are observables defined at collider experiments. So if you say something very high level, like there is quantum chromodynamics, which is an SU3 theory, what does that mean? What are the actual observables that tell you that this is the internal structure that is going on? So that is something that we will learn. We will learn how to simulate the production of new particles. So if you're looking for signatures of some new physics that we have not yet seen, what would that look like? How would you simulate that? If you do produce new particles, how would they decay? So they would normally, any new particles that you produce are not stable, but decay back into some standard model particles. So you would learn about that. And then there are some further details about simulating realistic collider environments. Okay, so that's the goal. Okay, so yeah, I should have changed this slide. So it's not, it has nothing to do with the final project. That was the idea last year, but I think since it's on Zoom, it's a bit hard to keep people on track. So there's not going to be a final project anymore this year. So this is just a list of things that we're going to do. Okay? Just a little bit of information about where to get more information should you need it. So this is a very, very important website for that. It's called PDG Live. PDG stands for Particle Data Group. And this page is continuously updated to include all the latest information that has been gleaned from any particle physics experiment anywhere in the world. So once it's published as a peer-reviewed paper, it gets added to this review of particle physics. So this is a snapshot from last year, but it should be fairly similar. So you can see all of the standard model particles are represented here, and you can click on any of them and you will get all the information about the particular particle, like its mass, its charge, if it decays, then its decay width, and so on. So the second useful information is about using Jupyter notebooks. So this is, I've found, by far the easiest way of learning how Monte Carlo works. So we are going to use these Python notebooks called Jupyter notebooks because they are sort of interactive. If you've used Mathematica before, they're sort of like Mathematica notebooks. And you can make plots in line, and you can use LaTeX in line and everything. So you can try it out here, but we will go through it slowly when we actually come to a lecture where we use it. So you don't have to worry about it if you have never used it before. Okay, so this is just a taste of what a notebook looks like. So you can import certain libraries for plotting or for doing numerical calculations. You can write LaTeX code in the following way. So you just type whatever you need, and then you can just generate random numbers if you need, which you will do if you're doing some Monte Carlo calculations, and you can plot it just in line that looks like this. Okay, that's just an example, Jupyter notebooks. And then we can start today's lecture. So this is sort of the plan for what we're going to cover today. So today is going to be extremely, extremely basic. And next week, we are going to review the standard model and the mathematics of gauge theories, essentially. And once we have that, then we have enough of a base to jump off to talking about collider variables and Monte Carlo and so on. Okay, so let me pause here and ask, does anybody have any questions?
Hello, ma'am.
Yeah.
Is it possible to do a term paper instead of the final exam?
I have not thought about this. Let me write it down and then I will get back to you if this is possible. I don't know actually.
Okay.
So, yeah. Okay. Yeah. No questions? Okay. Good. So let's start with the first thing that we have, and many of you might have come across this already, and that is to do with natural units. Okay. So in particle physics, we are dealing with some very unusual scales, which are not our intuitive human scales. So normally the size of the nucleus is of the order of 10 to the minus 15 meters, so which is also called femtometers or Fermi. Mass of the proton is about 6-7. So you can see that both these numbers are very small. So what we often do is we use these units. You may have come across this before, where you set h cross and c to 1. And then this essentially relates energy units and distance units and time units and all of them together. And we choose to describe everything in terms of electron volts, which you will remember is the energy that an electron gains when it is accelerated by in a potential difference of 1 volt. Okay, so we know that 1 electron volt is 6 10 to the minus 19 joules. So it's a tiny, tiny amount of energy, but this is the right energy scale for talking about what we want to talk about. Okay? So what does that translate into? So the most common unit that we will be using is the giga electron volt. Okay, so giga is 10 to the 9, and so 1 giga electron volt. So you can see that this is 1.6, and this so if 1 GeV is almost exactly equal to the mass of the proton, that comes out to the same number, and also GeV inverse comes out to be 60 meters, which is approximately 0.2 Fermi, which is the size of a typical nucleus. Okay? So these numbers are essentially very useful because if you talk in terms of GeVs, then you're at the right energy scale and the right length scale to talk about the phenomena that you want to talk about. Okay? So another thing that you can do here is you can convert this Fermi into GeV, right? The size of the nucleus is about 1 Fermi. So when you convert it to GeV, that comes out to about 200 MeV. So what does this tell you is that the energy that you would need to break apart a nucleus and look inside would be something like this. Something like this. So this would be the number. So which is why this kind of conversion is also useful, because in the same go, it also tells you what kind of energy you need in your system to be able to see what is going on inside. Okay? So that's natural units. Yeah, another fun thing you can do is you can ask, what is the length scale that the LHC can probe? So does anyone remember what the energy of the LHC is?
100 GeV.
13 TeV.
13 TeV. Okay. So yeah, again, so this is just for somebody who might not have encountered these units before. So you might have encountered milli, micro, nano. Milli is 10 to the minus 3, micro is 10 to the minus 6, nano is 10 to the minus 9. Then you have pico, which is 10 to the minus 12, and femto, which is 10 to the minus 15. And on the other side, you have kilo, which is common. Then you have mega, which is 10 to the 6, giga, which is 10 to the 9, tera, which is 10 to the 12, and peta, which is 10 to the 15. Okay. So currently we have phenomena that range from all of these, either length scales or energy scales. So yeah, so the energy of the LHC is 13 TeV. So you want to convert it into length, so you want to do 1 by energy here. So GeV inverse. So that would give you essentially 7 into 10 to the minus 16. That was the thing that you had. 10 to the 4. So this comes to 10 to the minus 20 meters. So that is the size that you're probing. So some very, very tiny length scales. Okay. So this tells you something about it in meters, but how much energy really is 13 TeV? So this is again just sort of an amusing fact. So 13 TeV, you want to convert it into joules. Okay, so that again, so the conversion factor was what, 10 to the minus 19. So this comes out to be 10 to the minus 6 joules, or about 240 kilocalories. So that's about the energy in a cupcake, or very popularly the CERN website advertises it as the energy of 3 mosquitoes. So if you take 3 mosquitoes and convert all the mass of the mosquito into energy, that is how much it would be, the collision energy of the LHC. the main thing that you have to realize is that all of this is squeezed into a very, very, very tiny area. So it's very high energy density, even though it's not very high energy per se. Okay, all right. So again, if you use these natural units, you have much simplification of all your equations. Okay. So you had this equation before, okay, and this just becomes, okay, because C is 1. And so you will normally just deal with all the masses and the momenta in GeV. That's what you do. Okay. Okay. Similarly, if you want to write down wave function, so normally you would have written it down something like this. And that would just become, so nothing groundbreaking happening here, but it's just to get us all familiar with writing things in a different way. Okay. All right. So next we come to this idea of scattering, which sort of is the fundamental way in which we define all our observables and the main way in which we do experiments. Okay, so can maybe someone tell me what they remember about scattering? What is scattering? No one? Okay, so let me ask, have you heard of this word before? Maybe use the yes no button. If you have not heard it before, please do use the no button, so then I'll explain in more detail. Okay. Most people have heard it before, it just seems that people are shy to speak up. Okay, so the idea of scattering is simply that you have, so right now we're just going to do 2 going to 2. So you have 2 incoming particles and 2 outgoing particles. And they may be the same, they may not be the same. Both of these possibilities exist. Okay. So there are a few things that we need to define just to get the names of things clear. So let's assume a simple system where you just have maybe some kind of target. So you have some kind of target block with some atoms inside, and then you have some other kinds of things hitting this block, and some of them get blown off their path and some of them just pass through. Okay, so this is normally how these scattering experiments happen. If you will remember from your high school physics, we learned about the Rutherford scattering experiment, which told us about the structure of the atom and the nuclei and so on. So this is the generic picture of scattering, and if you have these particles A coming from here, then you can think of phi A as the flux, which is essentially the density of particles times velocity. And then you have this block, so sorry, it's a bit asymmetric, which has width D, and then the area is say A. Okay. Then you can write down the total interaction rate dot as a product of the flux of A times NB, which is the number of scattering centers that you have, times some quantity called the cross section. Okay. So this n phi a we've already defined, and b is simply the density of these scattering centers in this material times the volume, so times A times T. Okay, so this is all very intuitive right now. So if you think of it in these terms, what this cross section is essentially telling you is, in some sense, the width of these guys here, right? So if it is of a larger width, then you would have a larger cross section. If it is of a smaller size, then you have a smaller cross section. So this is, in that sense, a geometric cross section. Something else happens if the particles A and B, so B, I forgot to write them here. So these guys are B's. Something else happens if both A and B are charged, which means that particles will feel their effect, each other's effect, even though they are not exactly geometrically overlapping, right? So you would have essentially an attraction or a repulsion even from a little bit of a distance. And then you can think of it intuitively as that the particle A sees particle B as being larger than it actually is. So cross section in that way can be a measure of the charge or the interaction strength between the two particles that you're probing. And this is why this is the most fundamental quantity that we use to make our observations. Okay. So this is the cross section. You can define sigma B. So if you can measure how many, what is the interaction rate, how many interactions are happening per second, then you can basically define the cross section using that measurement by just inverting the formula. You know what the density in B is, you know what the size of the block is, you know how many particles you're sending in the flux. This thing at the bottom is called the luminosity. Okay. So this is again that on the top you've just measured the interaction rate. Okay. And the other thing that you can do is if you integrate over time, so you run this experiment for some time t. So if you integrate over time, just the luminosity, this is what is called the integrated luminosity. So luminosity is often abbreviated as just lumi. And if you do this, sigma, this gives you the number of reactions, right? It's not, again, it's not non-intuitive at all. It's very intuitive. And in the sense of collider experiments, what this gives you is the number of events. Okay, so this is a word that you will see very, very commonly used, events. So each collision event is two particles coming together and something happening. Okay, so that's a collision event. So this was for a fixed target. So you can modify this expression for a collider environment as well. So your luminosity in that case would be NE, NB times V. I'll explain all of these in a second. Okay, so NA and NB are, as before, the number of particles A and B. V is the velocity of these particles. U is the circle. So this is for collider experiments where you have two beams that are circulating in a circular ring. Okay, U is the circumference. And P is the number of packets. So what happens in these kinds of collider experiments is that you have certain packets of, say, protons or electrons or what have you, whatever you are colliding, that have been filled into the ring. Okay, so you have NP number of packets that have been filled, and they are going around the ring with a velocity of v. I should say speed of v. The circumference of the ring is u. So the same formula can be translated in this way. Okay. So it's just a slightly different way of writing. Okay. Any questions so far? So there are two things that we defined here, or other three things. We defined the cross section, We defined what is luminosity and integrated luminosity. We defined what events are. And yeah, that's it. So these are the three things that everybody should keep in mind. Okay.
The
All right.
luminosity is constant, right?
The luminosity does not have to be constant, but yes, you design it so that it attains a constant value. So for experiments or other accelerators like the LHC, you start with injecting a few protons, then you inject a few more, then a few more, and you keep going until you reach a stable number.
Okay, so this integration, okay, it won't be trivial.
So sometimes, yeah. So it depends on what. So there are two things. So here when I'm talking about luminosity, I'm just talking about how many things are in there, and you can do data taking once you've stabilized. So you say we are not going to take any data until we've reached a certain flat value. That's also possible, but yeah, you can also be at a varying luminosity, and then yeah, it's sort of trivial in the sense that you normally this guy doesn't really depend on the luminosity, so you can actually take it out of the integral. So it's just cross section times the integrated luminosity.
Okay.
Okay. All right. So that's the first part. The next thing that we are going to sort of review again, some of you might know this already, is the kinds of scattering, and then just to try and connect them with the kinds of experiments that are running now. Okay, so the first thing that you would have heard of would be elastic scattering. This is the simplest kind. So you had A plus B going to C plus D. So elastic scattering is where your A is equal to C and B is equal to D. Okay, so the way it looks is simple. So you have one particle. So you have one particle hitting the other, and then they are just deflected from where they are. So this is also called billiard balls, hard sphere, many ways to think about it. Can someone tell me of an example of current experiments where this kind of scattering is used? Does anybody know? Okay, so let me tell you. So one of the places where this is used is for dark matter detection. Where the idea is that you have some fixed target with some heavy nuclei N, okay? And you would have some dark matter that would come from outer space, hit your detector and go away. And that hitting your detector would essentially modify your or just jiggle the heavy nucleus that you have in your target a little bit, enough that you can detect it. Okay, so that's how most of these direct dark matter detection experiments work. Okay, so that's where it is still used. That's the most fundamental way of, or rather easiest way of looking of thinking of scattering. The second one is what is called inelastic scattering. Where essentially your incoming particles are not the same as outgoing particles. And there are many examples of this happening. One example is in nuclear reactors, for example. So you have some heavy nucleus, you have some particle hitting it, which turns the nucleus into some other nucleus, which is even more unstable. and then that guy breaks into smaller pieces. And then if you have multiple of these guys being produced, that will also give you a chain reaction. So you will remember having seen something like this either in school or in your earlier undergrad years and so on. So this is one possible way of having an inelastic scattering. Another kind of inelastic scattering that's very useful for particle physics is what is called deep inelastic scattering. And this is used to probe structure of the proton or the neutron. So it's used to probe the structure of some composite object and to break it apart into its constituent parts. So that's the idea. So the way it looks like is something like this. So you have an electron that hits a proton. So the electron doesn't change. The electron hits the proton and this gets deflected, and you can measure the angle that it comes out at. But the proton itself will break into multiple constituents. This is just X. So this is normally written in the following way. So this is an example of another inelastic scattering process. Okay. So this we will learn in detail the mathematical modeling of deep inelastic scattering and how that is used to determine what are called the parton distribution functions, or the probability distributions of finding quarks and gluons inside the proton. Okay. So there's another example of inelastic scattering, and that is in neutrino detectors. And here is where you have neutrinos that come either from a reactor or from the sun or from some other source. And the neutrino turns into a charged lepton. So for concreteness, let's say a muon. And it changes the nucleus of the heavy nucleus that you have into something else. Okay, so this is sort of what the process looks like. So normally what you have as the detector material in this case is water. So you have this very, very stable reservoirs of water and kept in the dark, deep underground. And so if you have neutrinos coming from the sun, they would undergo this reaction and emit an electron or a muon, which you could detect in the detectors that line your reservoir and tell you that there was a neutrino here. So that's another example. Okay, so the final distinction that we need to make is between fixed target and collider. So again, I'm sure all of you have already understood by now what I mean by both of these cases. So in the fixed target case, you have a beam of incoming particles hitting some scattering centers that are held fixed in a material. And in the case of a collider, you have two beams that come in opposite directions. Okay. So this is what they look like. And for colliders, a useful frame of reference to work in is what is called the center of momentum frame. Where you have the momenta of the two particles exactly opposite to each other. So does anybody remember, or has anybody learned of why do we use the center of momentum frame?
And the 3 momentum is 0 in that frame. So
Yes.
calculations become easy sometimes.
Okay, that's a possible answer, yes, but there's more to it than that. Okay, so all right, so let's just write down so let's call this particle A and this particle B, and let's just write down the 4 momenta of the particles. So this is some EA, energy of A, 0, 0, B. So let's assume that this is the z-axis. Okay, so this is z, and the xy plane is sort of perpendicular to here. Okay, so that's the xy plane. And similarly, we have PB. Minus B, right? So if you look at the total momentum, or rather the total momentum in the system, you have EA plus EB and 0, 0, 0. Okay. So what does EA look like? We know from our earlier calculations, C is 1, so this is just MA squared plus B squared. EB similarly is MB squared plus B squared. So let's work in a regime where you are essentially accelerating the particles enough so that they have momentum much larger than their mass. Okay, so you can ignore MA and MB with respect to P. So MA and MB are much smaller than P. Okay, so in that case, you have P dot squared is simply 4 P squared, or P dot is equal to 2P. Right? Whereas if you had a fixed target experiment, then you would have EA same as before. EB would simply be NB 0, 0, 0. And in that case, your dot would be simply, or rather, so the energy that you have available for collision, oops. Would simply be P instead of 2P. So being in the center of momentum frame means that you have maximum possible energy to create new particles. Okay, so that's another reason why we work why we do experiments as collider experiments rather than fixed target experiments. Okay, so any questions so far? Okay, good. So since today is the first class, yeah.
I just wanted to know your comment on the Lorentz transformation behavior of the cross section from the definition that you had taken up.
So the cross section is always Lorentz invariant. I'm not sure I understand your question.
Okay, like means the way we are defining it for any generic Lorentz transformation, it will be Lorentz invariant. You are saying.
Yes. So
I'm saying because there are dimensionful quantities in the definition, so I was slightly confused as to like flux, and there is some things about the rate also. There is inverse time dimensions also.
Right.
So whether they compensate for each other, or is there something left out?
Yeah. So let me put it this way. Yeah. So your cross section in general is integration over phase space of some matrix element square, right?
Yeah.
And this guy is always Lorentz invariant.
Yes, this will be.
Right?
Yes.
So you're right in the sense that there is some dependence of the cross section on the phase space. Yeah, but Yeah, so that thing is obviously fixed by the parameters of your experiment, right? So if you have only certain energies available for collision, then you will only integrate over those energies, right? So you will have a different cross section than if you had a larger range of energies available for integration, and so
True.
on.
But that would be a frame dependent statement, right? That energy inputs will be different for different frames of reference. What do you do?
I'll think about that a bit more and get back to you. So
Sure.
on the surface, yes, it sounds right that you should have a different cross section. Well, yes, of course. So if you have a collision, can you mute yourself? So that is very noisy on your side. So on the whole, yes, I suppose you are right that if you perform the same kind of collision with a fixed target and with a collider environment, you will get a different number for the cross section. Yes, I think that would be correct to say. Yeah, but let me also think about it a bit more, because what I want to connect it with is sort of the fundamental charges of the particles themselves. So I'll make this a bit more clear in the coming classes. So there's something in the chat. Okay, good. All right, more questions?
Yeah, ma'am, I have a question.
Yeah.
When we say the integrated luminosity of LHC right now is, let's say, 139 femtobarn inverse, what do we exactly mean by that? I mean,
Okay.
from the luminosity expression that you gave.
Yeah. So for the LHC, what you can, so I find it more useful to think of it in the reverse. So for example, if you know of the cross section of a particular process, so for example, you have a PP collision and you're looking at a dimuon final state, right? And you can measure or rather the cross section of this particular reaction, then the number of events that you have total is this luminosity times cross section. So this obviously is the number of events that you observe, and this is the cross section that you extract based on this number of luminosity, which is measured and provided to you by the accelerator. And in that sense, they just mean this number here. This number here. So you have the number of protons in each of the beam, you have the velocity of these protons and the circumference of the accelerator, you have the number of packets that have been put in, and the area of the beam. So that's what they mean by luminosity. So this is the instantaneous luminosity per second, and then you have this 139 femtobarn inverse, which is basically this instantaneous luminosity summed over the total amount of time that they were running the accelerator or crossing the beams and making collisions at any of the experiments.
So it's like the exposure of a camera kind of.
Exactly. Yeah, that's a very good way to think about it, actually. So it's sort of like the exposure time of a camera. And in fact, since you've brought out this metaphor, there's actually another very interesting thing that the LHC experiments do, which is what they call the minimum bias or underlying minimum bias experiments, or the minimum bias measurements, which is where they don't actually put any requirements on the particles that are coming out of the interaction. They just observe blankly whatever is coming out and then use that to set the total cross sections. So that's just like keeping your camera shutter open and making a measurement to see what is the total cross section.
Okay, thank you.
Yeah, more questions? So yeah, also feel free to interrupt me at any time. So I mean, today's class was very, very basic, but when it gets more complicated, feel free to just interrupt and ask. Okay, so to end today, what I'm just going to tell you is about what is called the particle zoo, which is just basically enumerating all the particles that we have found so far. Just historically, the way these things have gone is people knew about chemical reactions, which led to us knowing about molecules. So each kind of chemical has an indivisible unit that gives it its chemical properties, which are called molecules, which you can break apart to have individual atoms, which are the characteristics of the individual elements, right? And then the atoms were split apart themselves, and we found that they were made of electrons and nuclei. And this guy was negatively charged, and this guy is positively charged. And we found that the nuclei themselves were made of protons, neutrons, right? And then eventually we find that these guys are actually not fundamental, but these are made of quarks and gluons as well. Okay, so these are the fundamental particles in question for us. These guys are fundamental, the electron is fundamental. Then there were further experiments. We found radioactivity. And in particular, we found beta decay, which led to the discovery of neutrinos. We were observing cosmic rays, which told us that there are more fundamental charged particles in the world. So for example, we found muons, and so on. So I'm not going to go through the whole history of particle physics right now. We will talk about the specifics as we deal with each of the sector of the standard model separately. But this is the total now picture of particles that we see now. Okay? So you can think of the standard model as a collection of particles, fundamental particles, plus the mathematical theory describing their interactions. Okay. So when you hear the phrase that something is standard model or not standard model, it can either mean that the mass or charge or some sort of property of the particle itself is different, or it can mean that the interactions between these particles are different from what was postulated. Or you can just add new particles. So that's all of the ways of going beyond standard model. Okay, so we have 6 categories of known fermions. And the fermions are divided further into leptons and quarks. Okay, so leptons, both of these come in what are called 3 generations of increasing mass in each generation. So you have the electron, neutrino, and the electron, the muon, neutrino, and the muon, the tau, neutrino, and the tau. And you have quarks, UD, up, down, charm, strange, top and bottom. Okay, so all of these particles may carry some electric charge. The quarks also carry polar charge. Yes, electric charge. electric charge only. So the reason I'm putting it in quotes is that the neutrinos do not actually carry electric charge, but they are charged under what we will come to know as SU2 cross U1. Okay, so that's the electroweak sector. Okay, so these are the known fermions. So there's 6 and 6, 12 of them, and then you have bosons, which are either spin 0 or spin 1. So there's only one spin 0 boson in the standard model, which is the Higgs. Okay. And for spin 1, you have the photon, the Z, 2 Ws of opposite charge, and the gluon. Okay, so all of these together make the electroweak sector. And this, the gluon is carrier of the color. Okay. So the modern picture that we have is that matter is usually made of these fermions, and the interaction between different particles of matter is carried by one of these bosons. So the electroweak bosons interact with anything that carries an electroweak charge, so they interact with both leptons and quarks. The gluon interacts only with objects that are color charged, so it only interacts with the quarks, not with the leptons. And the Higgs interacts with everything that has mass. And I'm going to put this in quotes because the nature of quantum corrections means that if it interacts with something that has mass and that in turn interacts with something that is massless, then you can have higher order interactions of the Higgs to massless guys as well. Okay, so that's why I'm putting it in quotes. But in general, you can think of it as the Higgs only interacts with things that have mass. And we will talk in detail about Higgs observables and what that tells us about Higgs parameters towards the end of the course. Okay, so that's what I wanted to tell you about the particle Zoo. And finally, I just wanted to chat with you about a few of the historical colliders that we have had so far. Okay, so the first one that I want to tell you about is the SPS. Okay, so the SPS is also at CERN, and it started operation in 1976 as APP collider. And it is perhaps the longest running collider because it still runs now. So it sort of acts like a mid-level booster before the protons get into the LHC. So you have a linear accelerator at first that accelerates the protons to some level, then it goes into some boosters. Finally, it goes into SPS that accelerates it up to 450 GeV. And then it goes into the LHC. Okay, to be accelerated even more. Okay, so it's still running. So this guy, or this particular accelerator, was one of the most, made some of the most fundamental discoveries. The main of this was in 1983, which was the discovery of U and Z. Okay, so this was by two experiments that were running at that time that were called UA1 and UA2. Okay, and in 1999, SPS also discovered CP violation in an experiment that was called NE48. So we know about CP violation in Madame Wu's experiments, but this was an independent measurement of that. Okay. So there are currently 5 running experiments also on SPS, which do various different things, from neutrino measurements to measurements of exotic decays of kaons and so on. So there's yeah, you can just look it up on Wikipedia. There's lots of interesting stuff there. And also another interesting thing is between 1981 and 1991, it was actually a anti-proton collision machine. So between so it was called the SPT bar S rather than the SPS. Okay, so that's the first one that I wanted to introduce you to. The next one is SLAC, which you might have heard of because it's also a very popular particle physics laboratory, a rather prestigious one at that. And they discovered the charm quark in 1976 and the tau lepton in 1995. Okay. The interesting thing about this guy is it's an E plus E minus machine and it's a linear collider. So so far we've been talking about these circular colliders where you have particles that are accelerated in a loop. So it's very space efficient. Whereas linear colliders require you to have a very, very large building so that you can accelerate particles to the required energy. So if you have a chance to go to Stanford and look at the SLAC building, you will see that there is a single building that runs over a kilometer long. And it was in fact named the ugliest building in America. It's a very there's nothing spectacular about it. It's just one single floor of a building. It looks like a go down, and it's just 1 kilometer long. That's that's what it looks like. So yeah, so this is, but it has made some very important discoveries. And another one of the discoveries made at a previous version called PEP was that of the gluon, which was also simultaneously made in Germany in the DAISY complex at an experiment called Petra. And here you had E plus E minus collision, and you looked at what came out of this collision, and you looked at jets in particular. So this is just a spray of hadrons like protons, neutrons, pions, what have you. And the way the way they discovered the gluon was they found events with 3 jets instead of 2. So 2 going to 2 is fully understandable, but 2 going to 3 was not easily explainable unless you postulated this extra particle. So again, we will talk about this in great detail when we talk about deep inelastic scattering and QCD. But just to give you an idea of this important accelerator. Okay. So then I want to tell you about HERA, which is again an experiment that was done in DAISY. So the D in DAISY stands for Deutsch, which means German. And it ran between 1992 and 2007. Okay, so it's fairly recent. And it was an electron proton collider. So far we've talked about proton-proton, proton-antiproton, or electron-positron. But this is a different kind of a machine where you do deep inelastic scattering. So this was the EP collision that I talked about earlier to basically measure proton distribution functions. That is to understand the internal structure of the proton. Okay, so this was an important experiment. Then we have LEP, which was the Large Electron-Positron Collider. So again, E plus E minus, and it was in the same tunnel in which LHC is running now. Okay, so it ran between 1989 to 2000. So it had to be shut down so that the things could be dismantled and the parts of the LHC could be put in the same tunnel. So it's a circular ring experiment. It started collisions at 91 GeV, And you will soon find out that this is because it's the mass of the Z boson. So it was originally envisioned as an experiment to make precision measurements by producing Z bosons on shell. And then it was extended to run at a higher energy of 209 GeV, where they tried to look for the Higgs boson. However, the sensitivity they had was to look for the Higgs, but only sensitive till about 114 GeV. That was the most that they could do. And we know now, in hindsight, Higgs mass is 125. So they couldn't find it at that time. But LEP has given us the most precise measurements of the electroweak sector that we have to date. So it's so the data from, or the results from the data from that experiment are still the cutting edge now. And then finally we have the Tevatron. So Tevatron is at Fermilab in America near Chicago. And it ran from 1983 till 2011. So again, till very, very recently, was a PP bar machine with maximum energy of 1.96 TeV in the collision. And when they started in 83, it was just 200. So they ramped up over time and we reached this high number of about 2 TeV. And they would also have produced the Higgs, but again, not in enough numbers that it could be seen as statistically significant. So they saw the Higgs after the fact, after LHC discovered it at about 3 sigma. Okay. Their main contribution was in discovery of the top quark in 1995. And mass of the top is about 175 GeV. So it's the heaviest particle that we know in the Standard Model, and was very, very difficult to discover it. And Fermilab also discovered the B quark in 1977. So that so they do have a tradition of discovering particles. So in fact, there is this small joke that all the fermions get discovered in America and all the bosons get discovered in Europe. So the Higgs, the W, the Z, and the gluon were all discovered in Europe, and all of the quarks were discovered in America. So people use that to make jokes about what the LHC can find. Okay, so that's everything that I wanted to tell you. And I just want to leave you essentially with a schematic picture of what we want to do in this course. Okay? So the idea is this. So you have the goal of the course is to understand PP collisions at the LHC. Okay, so you have two protons. We now know that they are not fundamental, that they are composite, and there are things inside them. So whatever is inside them normally interacts and generates something else. Okay. However, the process is not really that simple, but because all of the constituents are charged, you have lots of radiation that takes place from both incoming and outgoing particles. And because quarks themselves are not stable, they actually, in the end, form stable hadrons. Okay. So what you will see is like a spray of stable hadrons, which are called jets. These are hadrons themselves. Okay. And this is radiation. So if you actually look at an event at the LHC, you have hundreds of particles, possibly even thousands of particles that are being produced in each event. So you want a way of going from this simple 2 going to 2 picture. So we know how to calculate this part here using quantum field theory. So it's a 2 going to 2 process. You can calculate matrix element square. But that by itself is not enough. So you need a way to simulate the radiation. You need a way to convert the quarks and gluons that you have after radiation into stable hadrons. And then you need to define variables that you can compare easily to theory. So talking in terms of the number of hadrons or the number of positively charged hadrons or negatively charged hadrons might not in itself be a useful variable. Okay, so we'll talk about how do you define what are useful variables. I'll make the word useful also more concrete, and how to simulate this 2 going to 1000 process, and that is normally done by what are called Monte Carlo generators. Which use probability distributions that have been empirically determined from experiment to simulate each step of this process from one to the next. So you go from no radiation to emitting of one gluon, then go on from that gluon either splitting or whatever happens in that case. Okay, so step by step, it looks at each possible leg of the process, calculates probabilities, and generates and gives you events that you can look at and make reliable observables out of. And so that is going to be the goal of our course. So next week, what I plan to do is give you a review of the standard model. So we will be talking about the electroweak sector first. So that I think will take a couple of days. Then we will go on to talk about some Monte Carlo techniques, and we will write our own toy Monte Carlo generator. So that will take another couple of days. And then we can go on to deep inelastic scattering and understanding parton distribution functions and QCD. And then we'll finally have all the pieces in place to do a realistic LHC study. Okay, so any questions?
What is actually meant by the sensitivity of a collider? Like when you said that LIP was sensitive to like 114 GeV.
Right, that's a very good question. So sensitivity can be defined in many ways. So I was using it in a very hand wavy kind of way, just to mean the energy to which it could reach. Okay, so it's 209 GeV collider. We know the so we can maybe go into a bit more detail. So the main process that LEP used for looking for the Higgs was E plus E minus going to ZH. Okay, so this was the main process. So if you have 209 GeV and mass of the Z is about 90, that means the maximum that you can actually do for H is about what, 119 GeV, right? And then of course there are some, you also need to reach some minimum thresholds for the detector to be able to see you. And also when you are talking about producing a process, there's usually a threshold that deals with, so you remember for cross sections, you essentially have an integral over the phase space, right? So when you are very close in mass, so if you have only just enough energy to produce the particle, then you don't have a lot of phase space to integrate over. So you have a very small amount of phase space. So your total cross section is very, very small. So to be able to produce enough of them that you will actually see them, you have to have enough phase space as well. So first of all, at LEP, it just did not have enough energy to produce the Higgs because the maximum it could give was 119 and the Higgs is 125. But when you take into account the fact that the phase space is also much smaller when everything is squished together, it could only have seen the Higgs if it was 114 or lighter. That's what I meant.
Okay, thank you.
So you can also have other definitions of sensitivity. Like you can have, for example, you can produce a particle that's very, very light and you produce it a lot, but it is so light that it doesn't decay. So suppose you produce a new particle that's very light and it decays into E plus E minus, but the E plus E minus that comes out of it are themselves not very energetic. So even though you're producing this particle, the things that it decays into are not energetic at all. So you are still not sensitive to it. So that's another way of losing sensitivity. So sensitivity can have multiple meanings. Okay, more questions? Okay, then I think we can end here for today and we meet again on Monday at 2:30. So the same Zoom link should work. So I'm staying, so you guys can go. I'm just staying behind in case somebody is too shy to speak up and wants to speak up later.
Excuse me, ma'am.
Yeah.
Uh, are these timings flexible? Like, but flexible, I mean, like, is it possible to hold this particular class on Wednesday 5 at any other time? Because we also will have classes from 5 to 7:30, I guess.
Yeah,
at this time.
Yeah, actually that's the problem. So on Wednesday, there is a class between 2 and uh, 2 and 5. I don't remember, but something like that for QFT2, right? So that's the reason it was set at 5. So there might be some people who want to do that, and then after 5, I agree, some people have class after 5 as well. So normally what I will try to do is end about 10 minutes. So when is your class again? It's from 5 exactly?
Like, it's from 5, yeah.
Which one is this?
It's quantum mechanics 2. And then after that, just after that, we have another class, statistical. It would be better if like you could post a doodle poll or something, and we can probably put our free slots there, and then you can decide from there.
Okay, so okay, that's a good idea. So let me do that for at least for the TI for students to see if there is a free slot in that. Okay.
Also, ma'am, I wanted to inquire that like, will the exams for this course be more like project based, or like would it be like written exams or something like that?
Yeah, so I was thinking of just written exams. So the last time, since it was entirely online, what we did was it was a take-home exam. So students just got a question paper, you solve it yourself, and then scan it with your phone, and you send it back. So this time, depending on how the situation is towards the end of May, yeah, I think most likely it will be a take-home exam, similar to last time.
Okay, thank you.
Yeah. Okay, so I think there are no more questions, so I'll just end the meeting for everybody.